Hello everyone. In this lecture we will be discussing the implementation of variational autoencoders. So in the past lectures we have gone in depth about learning the concept of variational autoencoders. So now it's the time to execute it in practical. So we will see that how whatever theory we have learned and whatever the formulas that we have derived, what are their significance and what outputs we are obtaining by implementing that formulas over here. So let's start implementing variational autoencoder in Google Colab. So here what we will do is we will first of all discuss each of these statements in detail, and then we will execute the same statements in Google Colab. So let's start. So these are as usual the importing of the libraries which are required in order to run the program successfully. So they are important, so we have to import them first. So the next piece of code, basically we have a learning parameter, we have set it to 0.001. We have taken the epochs to be 30,000 and the batch size we have taken as 32. The network parameters here, please note that the image dimension we are taking as 784 because the size of the image, that is we are discussing MNIST dataset. So the size of each image in the MNIST dataset is 28 cross 28. That's why the image dimension is 784, which is multiplication of 28 into 28. So we are taking it as 784. The hidden dimension of the neural network, that is the hidden layer of the neural network, we are calling it as neural network dimension, and we are taking it as 512. And there is one more dimension which we call as latent variable dimension, we are setting it as 2. So let's see what are these dimensions actually. So if you see the neural network here, this is the input node of this neural network and the dimension of this is 784, that what we were discussing over here. So this neural dimension of 512 corresponds to this layer. So this is basically the layer that we are talking about, and its dimension is 512, and we are calling this layer as encoder layer. Similarly, we have a decoder layer also, so that dimension is also 512. So we will use 512 for this layer also. The next variable is latent variable dimension, and its value is 2. So what we are saying by that is this is basically the latent variables. So their dimension is 2. So we are using 2 neurons in each of these layers. This is the mu layer and this is the sigma layer. So the next thing that I will discuss is this. It's basically a Xavier initialization of the neural networks. It is similar to the initialization that we have done earlier also, and it's basically the initialization with random weights. And the motivation to initialize the neural network with these weights is that the neuron activation function should not saturate or become dead. So we want to initialize the weights with random values that are neither too small or too large. For that case we are using Xavier initialization, which comes in this format. So the size of this random normal will be the same size as what we are feeding in here, and the standard deviation is taken as the first dimension square root divided by 2. So basically it's taking the first dimension of this vector and dividing it by 2 and then taking a square root of it. So that will be the standard deviation of this particular random normal. So now we will define the dictionaries for weight and bias. So please note that we have here 5 weights and we have 5 biases. So these weights and biases corresponds to this particular network, where the weights are basically W1 for this node, W2 for this particular section for the mu vector, and W3 for this section for standard deviation sigma, then W4 for this and W5 for this. So you have 5 weights for this particular neural network, and the bias corresponds to, for this it is B1, for this mu vector we have B2, for the standard deviation vector we have B3, then for this vector we have B4, and for this decoder we have B5. So we have these 5 bias vectors and 5 weight vectors for this particular variational autoencoder. So in that case I have defined the dictionaries in that same sense. So please have a look onto these dimensions, which is very important. So these dimensions, the discussion about these dimensions I have already done in our earlier lectures also. So you can just see how these dimensions are defined. The next section is building the computational graph for this TensorFlow. So the first thing is we need a placeholder which take input in the form of shape none and image dimension. So basically it is taking input as an image of database having the dimension as 784 none. So this none means the number of images present in the dataset, and this 784 is the flattened version of 28 cross 28 image. So image underscore x will take this as the input. So that's why we are defining it as placeholder, and it will take the value as float 32. The next thing is to define the encoder layers. So this is also very important. And this encoder layer is basically defining this layer. So we are defining this encoder layer, and how we are doing it? We are doing it by taking image x as the input, and then we are multiplying, and then we are matrix multiplying it with the weights, and then after obtaining the multiplication of the image x with the weights, we are adding bias to the result, and then we are passing the whole encoder layer into the nonlinearity, that is the tan hyperbolic nonlinearity, and then it will result into the output as encoder layer. So we will get something at the output over here as the encoder underscore layer. So once that is done, then we will create two different layers of mean layer and standard deviation layer, which is defined over here. So this is the mean layer and this is the standard deviation layer. So we are defining these two in this statement. So mean layer is defined like this and standard deviation layer is defined like this. So this is also easy. You can see how we are passing the encoder layer output inside, and then we are multiplying that with the weights and adding it to the bias. Similarly, the standard deviation layer will also take encoder layer output and then multiplying it with the corresponding weights of that standard deviation layer, and then adding the bias corresponding to that standard deviation layer. So this results into the two different layers. So now comes the concept of reparameterization trick that we have already learned. So in that case, what we have to do is you have to generate epsilon naught from the random normal distribution with the shape as that of the standard deviation layer with mean 0 and standard deviation as 1. So this is generating epsilon naught from the random normal distribution of n 0, 1, and this is what it is doing is it is implementing the latent layer, which is z in our derivation, equal to mu plus sigma half times epsilon naught. So this is what it is doing over here. But please note, here we are having the definition defined as mu plus exponential to the power of half sigma times epsilon naught, but this is not the same as this. Why we have written like this? Because as I told you that we are taking sigma as log of sigma. So in that case, if you reduce this, it will come out to be what? Exponential half log of sigma times epsilon naught. So if you solve it, it will come out to be mu plus sigma to the power half times epsilon naught, and that is the same as this. So it's just another way of representing the same expression using this. So this latent layer is defined in this part, and next what we will do is we will feed this latent layer output into the decoder input. So that's why we are defining a decoder hidden layer which takes input as the latent layer output and multiplying it with the corresponding weights of that hidden layer, and finally adding it together with the bias corresponding to that decoder hidden layer, and then passing the result to another nonlinearity of tan hyperbolic. We will obtain a decoder hidden output, and this decoder hidden is basically this part of the network. So now once this is done, we have to obtain the output. So that output can be obtained by using decoder output layer, which takes input as decoder hidden, which is evaluating from here, and then multiplying it with the corresponding weights and adding it the bias, and finally we are passing it through the sigmoid nonlinearity in order to generate the decoder layer output. So this is basically the reconstructed image that we obtain at the outside here. So this is basically the reconstructed image. I hope I am able to make you understand about this computational graph. So once this is done, now the time has come to execute the computational graph. So before executing the computational graph, one more thing that is very important to be defined is the loss function, because you know in every neural network we know that we have to define the loss function, which we have to optimize using any optimization techniques. So in order to do that, let's define the loss function for this variational autoencoder. We know from the theory that the variational autoencoder loss function consists of two parts. One is the reconstruction loss and the other is the KL divergence loss. So we have to implement these two and sum them together in order to find the complete loss. So what the reconstruction loss is written over here is as a data fidelity loss. So the data fidelity loss is defined like this, which is original image times log of reconstructed image plus 1 minus original image times log of 1 minus reconstructed image, and then we are doing the reduced sum of this data fidelity loss to get the complete results. So as you may recall that the reconstruction loss is defined like this in the standard text. So what we are doing is we are implementing the same over here. So this is basically the cross entropy loss which we have adopted over here. The next is the KL divergence loss which we have defined over here, which is 1 plus standard deviation layer minus this minus the exponential of the standard layer. So if you see this closely, it is similar to this expression, except that this expression is minus of this expression which I have written over here. But that minus is taken care of in the second part, which is I have taken as minus of 0.5. So, and this you already know from our theory where we have derived this expression. So it's just same expression. So this defines the KL divergence loss. So the next is what we are doing is we are actually weighting this data fidelity loss and KL divergence loss by two variables that are alpha and beta, and then I am putting alpha is 1 and beta as 1. I will tell you what is the reason for doing that later on, but what I am trying to achieve here is that suppose I want to show you the results when only data fidelity loss is there and there is no KL divergence loss, and if data fidelity loss is not there and only KL divergence loss is there, and if both of them are there. If you recall, I have discussed this in theory that what kind of impact that creates in the reconstruction, but the same thing I want to implement in practical also. That's why I have weighted it by alpha and beta. If you don't want to work on this exercise, you can put simply alpha and beta as 1, but for my case I want to show you the visualizations that comes out from this and what kind of results you can deduce from that. That's why I have kept alpha and beta as variables over here. So the loss value we have defined as the loss function. So we are calling this loss function with image input and the decoder output layer, which is the reconstructed image. This variable decoder output layer is defined this part of the code, and then we are optimizing the whole thing using RMS prop optimizer with the learning parameter, and we are minimizing this loss value which we have defined. So this initializes the variables that we have defined in our case. So now the step has come to execute the computational graph, and this is done through calling this session. This initializes the variables. So this we are taking as 30,000. So I is running from 1 to 30,000, and then for each 30,000 run we are taking the batch size of 32 of the training images, and we are feeding them into x underscore batch, and this batch is feeded into the image underscore x placeholder, which helps in evaluation of the optimization and the corresponding loss, and we are printing the loss for each iteration for every 5,000 runs. So once this is executed, our variational autoencoder will be trained, and by saying training means our p theta of x given z and q phi of z given x will be trained, and by saying training means their theta and phi will be trained. So now we have to test our trained network, so that in order to see whether our variational autoencoder is able to generate the data or not. In order to test the variational autoencoder, what we will be doing is we will create a placeholder of float 32 type, and this is none, and this is the latent variable dimension, that is equal to 2 in our case. So we will create a placeholder that will require input from outside, and we will call that as noise underscore x, and then we will again rebuild our decoder which we have defined earlier, but the only difference is that we will now input here as the input as noise underscore x, and it is not the earlier input which was latent layer, that is here. So it will not be this, it will be noise underscore x. So once that is done, we will execute the computational graph. Here I am just repeating again the testing phase of our variational autoencoder. In testing phase, we do not require this part of the block, that is q phi z given x, and the only thing that we need is this part of the code, that is from here to here. And what we are doing now will be, so we will be generating x hat which belongs to the similar family of x, but will not belong from the data set. Suppose this is the data set of x, then the x hat will be belonging to the same family but some other samples, these green ones, which are not in the data set. That's why we call this as the generator model. So for that, what we do is we will feed in the sampled values from the Gaussian, do this transformation, and once that transformation is done, it produces the z latent vector, and this z latent vector will be fed into this generator model, and once that is done, it will generate new samples of the data. So let's see how we can do that. that. So now we will be doing the output visualization. It means we will be seeing how the data is generated. So this is done through this block of code which we are showing over here. What we are doing is we are taking n as 20 and then we are taking a range of linear space between -2 to 2 with 20 samples in between them, and then we are creating an empty image of size 28 cross 28 times n, 28 times n. This is just for displaying purpose. Then the important thing is this part of the code where we are generating some samples. Here once we generate the samples, we will be feeding that into the ses.run command, which operates on decoder underscore output layer, which is the layer which will generate x hat, and it takes input as generated underscore latent underscore layer. So once that is done, we will obtain this image, and this image corresponds to the command that we are running over here. So this visualization shows that the distinct digits are available in different regions of the latent space. What does it mean? That we have distinct digits in different regions of the available space. You can see that this is a distinct digit in this region of space, and the thing is there is a smooth transformation from 0 to 2, which is another region which can be observed from this output. So you can see that how 0 is smoothly transformed to 2, which is again smoothly transformed to 6, and then 6 goes to 9, and from the downside it is going from 0 to 5 over here, and then 3, and then 8. So it's a smooth transition in this side and a smooth transition in this side. If we want to plot this graph, which is not the type of graph over here, but what it is showing is just the generated samples which are not in the MNIST data set, then what we do is we run this line of code, and this line of code is doing what? It is just sampling the data from the normal random variable and feeding it into the decoder underscore output underscore layer. So once that is done, it will generate this result. You can see that these digits which are generated over here are not from the MNIST dataset. They are generated from random noise. So this is the interpretation of the results for the variational autoencoder. There is one more way of interpreting the results, and they are like, if you want to visualize that how the digits are generated depending upon the latent space dimension, then you can see you have this following pattern. It shows that if you use L is equal to 2, that is the length of the vector Z as 2, which is the latent space dimension, then the results are a little blurry. You can see you have some blur appearing on the edges of the image. Whereas if you take the dimension of Z as 10, then what will happen is a bit sharp images compared to that in case of L is equal to 2. And if you increase the dimensions to 24, then also the quality gets a bit reduced as compared to L is equal to 10. So these variations of different L are obtained by changing this dimensions from 2 to 10 to 24. So by doing that, you can observe these results. So the next part of the visualization that comes into play is the visualization of the cost functions. As I discussed earlier also that the cost function consists of data fidelity term plus the KL loss term. So we want to see what kind of outputs we obtain for different combination of these two terms. So in the first combination, if we have data fidelity term and no KL loss. In the second combination, if there is no data fidelity and KL loss is there, and in the third combination if both are there. We want to see what kind of results we will obtain if this situation is there. So in order to implement this, what we have to do is we have to run this block of code, and in this block of code, please note that we are taking test data set over here with the testing samples as 15,032 because we have taken batch size as 32. So the test samples comes in x underscore sample and the corresponding labels comes in y underscore sample. So now what we will do is we will run the latent underscore layer. So we will run the ses.run on latent underscore layer, and what that latent underscore layer is doing is, if you go back to the code, what it is doing is it is implementing this part of the code where it is sampling the data from the standard normal Gaussian 0,1 and then applying the transformation, which is this. So basically we are getting samples of the corresponding MNIST test data set, and we are putting it in latent underscore layer variable. In order to see the impact of data fidelity and KL divergence, we are incorporating this alpha and beta. So if alpha is 1 and beta is 0, then we will have only the data fidelity term playing the role, and if beta is 1, then we will have KL divergence playing the role, and if both are 1, then we will have both of them playing the role. So on that basis we have executed the graphs that we are showing you now. So in this case, what we are showing is only the reconstruction term is playing the role. In this case, our beta is 0. You can observe here that we are getting the clustering of the digits, and the clustering of the digits goes in such a way that 0 corresponds to these number of digits, and 9 is, as you can see, 9 is a bit here, so this corresponds to these digits, and 8 corresponds to this digit. So you can observe that there is basically clustering of the data point. But the problem with this scenario is that there are some vacant spaces available here. So what happens is that suppose this is basically your 8 and this corresponds to 0. So if you want to interpolate between these two, and suppose sample latent variable falls somewhere here, then you don't have any knowledge about the distribution of this particular sample. So that's the problem, because if the sample falls over here, then the distribution is unknown. That's why if the loss contains only reconstruction term, it will be a problem, because the interpolation between 8 and 0 is missing because of the unknown distribution in this area. That is why you are getting some problems over here. You can see some noise is coming, and in similar way you can see some noise appearing here and here. These are all transition regions. So in transition regions, you don't know the distribution in that area. So maybe for this part of the thing, it lies over here and you don't know the distribution at this point. So that's why it's giving as a noise. So only reconstruction term will not help in achieving better generated samples. Now here we are using only KL divergence term, in which only beta is 1 and alpha is 0 in our codes. So you can see that the pure KL divergence loss results in a latent space in which the encodings are densely placed randomly near the center of the latent space. That is, it is packed densely over here with little regard for the similarity among the nearby encodings. So the decoder finds it's impossible to decode anything meaningful from this space simply because there is really anything not meaningful over here. That's why we get noise in the results. So we are not observing anything over here. So all noise. The third part of this is where alpha is also 1 and beta is also 1. In this case, you can see that when we are optimizing both of them, the results shows that the generation of the latent space maintains similarity of the nearby encodings on the local scale via clustering, yet globally they are very well densely packed near the latent space origin. So you can see that they are all packed nicely. You can see that the clustering is happening in a very nice way. So if you want to generate anything over here, then which is not from the sample space, then it will interpolate between the distributions of this part, and it will generate a new sample here which is not from the existing data set. That is the MNIST data set. So these are the corresponding results. You can see all these data which are generated does not belong to MNIST data set. They are completely new. So this completes the theoretical understanding of the code along with the execution results. So we will quickly go to the Google Colab and execute all these results and show you that these results are indeed working in real time also. So now we will discuss the implementation of variational autoencoders in Google Colab. So now you can see that I have opened the same code which we have explained each and every line of it in theory on Google Colab. So let's execute these lines of codes one by one. So this is just importing of the library. So let's run this. So you can see it's executing. So now it's executed. This is importing of the MNIST data and we are putting it into the variable database. So let's run that. So it's executing and unpacking the data from the TensorFlow examples. So now you can see that it is done. You can check that here on files. Just go and refresh the button. You will see that the MNIST data is in this data folder. So once that is done, now you define the learning parameter epoch and batch size, the network parameters that we have already discussed in detail. These are the latent variable dimensions. This is the Xavier initialization that is being done in this program. So let's execute this. It's executed. These are the weight and bias dictionaries that we have discussed in greater detail in the theory. So let's execute this. It's executed. And this is basically building up of the computational graph. Here we have this image X as the placeholder. These are the encoder layers. These are the mean and standard deviation layer. This is the reparameterization trick that we have discussed in greater details in our earlier lectures. So this is the epsilon naught that we are sampling from the normal distribution, and this is the latent layer that is executing the mu plus square root of sigma times epsilon naught. So this is basically the linear transformation that is carried out. So this is the latent layer. Then we have a hidden layer in the decoder section, which takes input as the latent layer and produces the output as decoder underscore hidden, which is then feed into again another layer which produces the final reconstruction output with sigmoid nonlinearity. In the earlier cases we were using tan hyperbolic nonlinearity, so you just check, you can play around with these nonlinearities. It's not compulsory to use tan hyperbolic, you can use ReLU also. For my case I have used these nonlinearities. So let's execute this. Once you executed this piece of code, the computational graph is created in TensorFlow. So this is the loss function that we have discussed in greater details. This is the data fidelity loss, this is the KL divergence loss, this is the total loss, which is the summation of the data fidelity and KL divergence with alpha and beta currently taken as 1. This is the loss value. So the loss value is basically, we are calling the loss function which is defined over here with the inputs as image x, image underscore x, which is the placeholder for which input will be given from outside, and this is the decoder output layer, which is the reconstructed output that we are obtaining from here. So now we have this optimizer which is optimizing this loss function with the learning parameter as 0.001, which we have defined here. So let's execute this part of the code. So now this is executed. Now the time has come to execute the computational graph, for which we are running the session, initializing all the variables, and then printing the loss for each of the batches that we are printing. So we are taking batch size as 32. So let's run this for 30,000 epochs and see what kind of loss we are getting for each iteration. So let's run this part of the code. So as you can see that the loss is being printed out for iteration 0 as 657.75, and let's wait for more iterations and see whether the loss is going up or down. So now you can see at the 5000 iteration the value has reduced to 159. So this will continue till 30,000. So let's wait for that time, and once it is completed we will come back. So now you can see that the loss is printed out for each iteration, and we can see that up to 25,000 it has printed out the loss of 144, which is very less compared to 657. So the loss is going down with each iteration, as you can see from the printed loss over here. So now the time has come to test the variational autoencoder. So in order to test it, we are again creating a placeholder with float 32 as the input values that it has to take, and the dimensions as none and latent variable dimension. Please note that this is latent variable dimension which we have defined earlier, that is equal to 2. But in case of this part of the code where we trained it, it is image underscore x, which is a placeholder having the dimension as image dimension. So this is the training phase where we are feeding the data from outside having the dimension as none and image underscore dimension during the training phase. But during the testing phase, this is changed to the dimension of latent underscore variable underscore dimension, which is 2. So this is important. So now we are feeding the data in the form of noise, not in the form of image. So we will rewrite the decoder section again with taking noise underscore x as the input. Earlier it was something else. So now we are putting noise underscore x as the input, because this thing we have already discussed in the theory. So you can check that. So once this is done, our output will be reconstructed from noise and it will be stored in this variable. So now the time has come to visualize those things. So this thing we have already discussed. So let's run this and see how the visualization is coming up. So we have not executed this part of the code, so let's execute this first. Now we will run this. So you can see how beautifully the data is generated from the noise, and you can see that the clusters are formed for the similar numbers and how that similar numbers are changing to other group of similar numbers slowly. So here you can see that how 7 is slowly changing into 9, and this is a small cluster of 7 and this is a small cluster of 9. And here from downside you can see how 7 is changing slowly to 1, and from 1 it is changing slowly to 8 and then 5. So this is basically a visualization space showing you how the data is changing across x and y direction. And if we run this part of the code, which is basically I'm sampling the values from the Gaussian distribution. So if we run this part of the code, then what will happen is, let's execute it. So then you can see different data generated from noise. So this is a different view of showing that same phenomena, but now these all numbers that are generated over here are not present in MNIST dataset. They are different. They are not the same as that of MNIST dataset. So that's why it's a generator network which generates different number of MNIST data. So this is the thing. So the next thing I wanted to show you is the scatter plot of the latent dimension. Let's plot the scatter plot for this latent dimension. So you can see that the scattering plot of the latent dimension, that is Z, is given over here, and you can observe that how beautifully the clusters are formed for individual numbers. And if you want to interpolate between the two, you still have some information in between them so that the new numbers can be generated easily between the two interpolated values. So this is coming because of the reason that we have taken as alpha and beta both as 1, which is shown over here. So if you want to run other parts of the code which I have shown you for this graph, that is only for KL divergence or only for the reconstruction loss, then you have to play with alpha and beta and rerun this program of code, and you can see it will change accordingly, and even these results will also change. They will not be same as they are looking now. They will not be the same, and the results will not be that clear as it is clear in case when both the terms are used. Thanks for watching my lecture. See you next time.